Hello! So today I'm going to talk about periodic trends, atomic size, ionization energy, and metallic character. So atomic size. The atomic size of an atom is determined by the distance between the outermost electron and the nucleus. So we all know that in an atom, it has a nucleus and then surrounded by an electron. So let's take a look at a hydrogen. So hydrogen, this is like the nucleus, and it has like proton and neutron inside, positive charge. And then this is the electron. The outermost electron is 1 electron for hydrogen. So the distance is between this nucleus to the electron. The same thing with lithium. For example, lithium, imagine this is the nucleus, and then this is the first energy level, so it has 2 electrons, and then another energy level which is another electron. So this is the second energy level, but also the outermost electron, because lithium has 3 electrons and 2 is on the first energy level. So from nucleus to the outermost is the atomic size. The atomic size decreases as you move across the period to the right in the periodic table, basically this way to the right. The reasons why it decreases as you move to the right is because that each step to the right, for example, going from sodium to chlorine, from sodium to chlorine, you add a proton. So the number of protons in the nucleus is increasing as you move from one element to another element to the right. This increase in the number of protons, it results in a greater pull on the electrons from the nucleus, causing the atomic size to actually decrease. Let's look at lithium. So imagine lithium. This is like the proton, like the nucleus has the proton and neutron, and then this is the electron. So lithium has 3 electrons. So this is how it looks. But if you look at, for example, carbon. So carbon, this is like the nucleus, and then you have proton and neutron as well, like lithium. So the proton is like 6 proton, and then you have the electron. The first one 2 electron, and then the second one you have 4 electron. If you look at the difference between lithium and carbon, so if you move across a period to the right, you increase the number of protons. So when you increase the number of protons, they are causing a greater pull, like because proton, which is the positive charge, always wanted to attract the negative charge from the electron, right? So when you have a lot of proton, it's going to pull electrons closer to itself. So when it does that, it's going to cause the atomic size to decrease. So whenever you move across the period to the right, you increase the number of protons, which cause the atomic size to decrease. The atomic size increase as you move down a column or a family in a periodic table. So if you move down this way, the atomic size is going to increase. So the idea is that as you move down a column, the energy level is increased. The size of an orbital increases with increasing energy level, which makes the electron that occupied the outermost orbital are further away from the nucleus as you move down a column. So imagine if you have hydrogen here, which is the first energy level, and then you have lithium, and then there's sodium. So as you move from first energy level to second to third, the number of electrons is further away from the nucleus. So the nucleus, imagine this is the nucleus, this is the nucleus, and this is the nucleus. So if you move from first energy level to third energy level, the atomic size increase. So this is like the trend. It decreases across the period to the right and increase down a column. Another way to remember this is that it's going to increase to the left and then down a column, so both increase. So you can just remember it as, if this is a periodic table, you can just remember it's this, like that. So when you draw it like this, it means that to the left increase, down increase. Okay, so let's do some example. Between carbon or fluorine, which one has a larger atomic size? We know that atomic size decrease across a period to the right. Carbon is right here and fluorine is right here. So carbons would have a larger atomic size than fluorine. How about lithium or potassium, silicon or nitrogen, selenium or iodine? Which one has a larger atomic size? So you can pause this and try this yourself. We know that atomic size increase down a column. So between lithium and potassium will have a larger atomic size than lithium. Silicon or nitrogen. So silicon is here and nitrogen is here. So we know that between nitrogen and silicon, we have to move down, which means that the atomic size increase, and then to the left, silicon is to the left of nitrogen, which also make atomic size increase. So both increase, which means that silicon has a larger atomic size than nitrogen. Selenium or iodine. The selenium is here and iodine is here. So moving down a column, the atomic size increase. However, iodine is to the right side of selenium, so you have to move to the right of the periodic table, which make these decreasing. So you have one moving down, which is increase, and then move to the right is decrease. Both of these going to end up cancelling out each other. So between selenium and iodine, you cannot tell which one has a larger atomic size. So cannot tell. One thing to keep in mind is that whenever you have an element that is moving down a column and then moving to the right across the periodic table, you cannot tell which one has a larger or smaller atomic size. Ionization energy. So the ionization energy of an atom is the energy required to remove an electron from the atom in a gaseous stage. For example, ionization of sodium can be represented, so sodium plus ionization energy, and you remove an electron, so sodium plus 1 electron. So ionization energy increase as you move across a period to the right in the periodic table. So remember that increasing ionization energy means that it is difficult to remove the electron. So let's look at sodium and chlorine. So we know that sodium has an electron configuration of 1s2, 2s2, 2p6, and 3s1, while chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, and 3p5. So between sodium and chlorine, it would be easier to remove these 1 electron rather than to remove 1 electron from the 3p orbitals. This is because chlorine is 1 electron away from having a noble gas properties, like it would want to gain electrons to be stable as a noble gas rather than want it to lose an electron. So another way to look at this is the same as an atomic size. So when you move across the periodic table to the right, the number of protons increase. So when the number of protons increase, it's going to increase the pull of attraction to the electron. So the electron is going to pull closer to the nucleus. So when something is pulled closer to the nucleus, it makes it hard for you to remove that electron rather than an electron that are held less tightly. Imagine hugging a ball and then just holding a ball. So when you hug a ball, it's held really tight to yourself, right? So it's going to be hard for someone to remove it from you. But when you just hold a ball, like for example, you can hold it in one hand, it's going to be really easy for someone to take that ball away from you. It's the same thing. If you have the electron held tightly to the nucleus, it's going to be difficult to remove that electron rather than the electron that held less tightly. So as you move across the period, the ionization energy is going to increase, which make it harder for the electron to be removed. Okay, so ionization energy decrease as you move down a column of family in the periodic table. So it's going to decrease down. So the same thing as an atomic size, as you move down, the energy level is going to increase. So when the energy level is going to increase, it makes the outermost shell, like the electron in the outermost shell, to be farther away from the positively charged nucleus, and therefore it's going to be held less tightly as you move down a column. If you have like hydrogen nucleus, proton, and then the electron like this, and you compare it with like sodium, so sodium, your proton, and then there's your electron, and you have your electron. So between hydrogen and sodium, so this electron is going to be easier to be removed rather than this electron, because this one is really farther away from the positive charge or nucleus. So you can just remove it easily. But this one is really close to this nucleus, so it's going to be held tightly rather than this electron from the sodium. It's the same thing, the same analogies like I mentioned. It's like between hugging a ball and just holding a ball with one of your hand or both of your hand. So it's going to be easier to remove these electron rather than these electron as you move down a column, because you increase an energy level. So this is like a summary of ionization energy trend. It's going to increase to the right and decrease down a column. Another way you can remember it is it's going to increase up and then increase to the right. So you can be reading it as something like this, which is represent up to the right. Let's do some example. So which one has a larger ionization energy between potassium or chlorine, lithium or rubidium, sulfur or iodine, and nitrogen or silicon? You can pause and try this yourself. So potassium or chlorine, potassium is here and chlorine is here. So moving down means that ionization energy decrease, and then to the left it's also decrease. So chlorine will have a higher or larger ionization energy than potassium. How about lithium or rubidium? So lithium is here, rubidium is here. So ionization energy decrease down a column. So rubidium will have a smaller ionization energy than lithium. So lithium will have a larger ionization energy. Sulfur or iodine. So sulfur is here, iodine is here. So moving to the right, increase ionization energy, and moving down, decrease ionization energy. So like atomic size, one is increasing, another is decreasing. So both of them is going to end up canceling out each other, which make it difficult to tell whether sulfur or iodine, which one has a larger ionization energy or a smaller ionization energy. So cannot tell. So this is like something you can also remember, like atomic size. If it's moving to the right and then going down a column, it's going to be about to canceling out each other and you cannot tell. How about nitrogen or silicon? So silicon is here, nitrogen is here. So you're moving down means that it's going to be decreasing, and then to the left also decreasing. So overall, silicon will have a smaller ionization energy than nitrogen, which makes nitrogen having a larger ionization energy than silicon. Okay, so let's move on to metallic character. So metallic character decrease as you move across the period to the right in the periodic table. So if you remember, metals tend to lose electron, like they wanted to lose electron, and then non-metals wanted to gain electron. And also, across the periodic table, ionization energy increase. So when ionization energy increase, it's going to make it harder to lose an electron, which make metallic character to decrease. Metallic character increase as you move down a column or a family in the periodic table. Ionization energy decrease as you move down a column or a family. So when ionization energy decrease, it's going to make it easier to remove an electron. So when it is easier to remove an electron, it's going to increase the metallic character. So this is like a summary of metallic character trends. You can also understand it that it's going to increase to the left and also increase down a column. So you can remember this way, increase. This is just like an alternative way to remember the metallic character trends. So let's do some example. Between magnesium or phosphorus and beryllium or barium, which one has a larger metallic character? So magnesium is here and phosphorus is here. Metallic character decrease as you move to the right, which make magnesium to have a larger metallic character than phosphorus. You can also look at it as a metal and a non-metal. So for sure, metal is going to have a higher or a larger metallic character than a non-metal. Beryllium or barium. So beryllium is here and barium is here. So metallic character increase down a column. So barium is going to have a larger metallic character. So let's do some more example. Arrange these in order of increasing atomic size. So I circle all of the elements here in the periodic table. We know that atomic size increase down and decrease to the right. At the same time, we can also remember it as it's increase to the left. Since we are arranging this in increasing atomic size, I wanted to work with the increase to the left. Okay, so if you look at all of the elements on the periodic table, rubidium is in the 5th energy level, which means that rubidium is going to be the largest. So we know that rubidium is going to be the largest. And then fluorine is on the 2nd energy level, so it should be the smallest. Now we can look at the 3rd energy level, so silicon and sulfur. So silicon is the left side of sulfur, and moving to the left means that it's going to be increasing in atomic size. So we know that sulfur is going to be smaller than silicon, so it's going to be sulfur and then silicon. And then we have calcium and germanium. So calcium is to the left side of germanium, which makes calcium to be having a larger atomic size than germanium. So germanium is going to be here and followed by calcium and then rubidium. So let's do another example. Arrange these in order of increasing ionization energy. So what we should do first is identify where is the element on the periodic table. So I circle all of the elements here. So we know that ionization energy increase to the right and then decrease down, or you can also understand it as increase up. since we are arranging this in increasing ionization energy, I wanted to work with just like the increase and the increase. So it's like it's going to increase like this. So if you look, we know that lead PB is going to have the lowest ionization energy, so it's going to be the smallest one. So after lead, we can look at tin or tellurium. So tin and tellurium is to the right side of tin, which means it's going to be having a larger ionization energy than tin. So followed by lead, it's going to be tin and then tellurium, and then we have sulfur and chlorine. So between sulfur and chlorine is going to have a larger ionization energy than sulfur. So this is the answers of this question. Okay, so one last example. Arrange these in order of increasing metallic character. So this is all the elements. I circled them in the periodic table. So we know that metallic character increase down and then decrease to the right, or you can look at it as increase to the left. So we know that francium is right here, so it's going to be having the largest metallic character. So francium, and then sulfur is here on the third energy level, so it's going to be the least metallic character. So sulfur, and followed by selenium, and then we can look at indium and antimony. So indium is to the left side of antimony, which means that indium will have a larger metallic character. So followed by selenium, we have antimony and then indium, and then what's left is barium. So this is the answer. Okay, so basically to conclude is the atomic size is going to increase this way. The same thing with metallic character. So atomic size and metallic character, and then ionization energy is going to increase this way. You can also understand it the same way that I've mentioned before, but this is like a shortcut if you want to just remember which direction is increase. So it's like increasing down to the left, increasing up to the right. So that's it about this video, and like I said all the time, practice make perfect. It doesn't matter how slowly you go, as long as you do not stop. Your progress is your own progress. Remember that. Bye.